As one of only two who tried the big zinger problem. Oh, additivity?
No, the one above it.
Homogeneity. Yeah.
Fancy writing.
All right. Also, we have this property is called monotonicity. If your function is non-negative on the entire region you're integrating over, then the integral has to be non-negative too. In fact, the only way it's going to turn out to be 0 in this case is if a function is going to be 0 on the entire region. And from that, you can get this conclusion. Suppose that your function is bounded by little m and big M on the region D. Then what you can do is you can bound the integral over D. So it's bounded above by the maximum value times the area of D, bounded below by the minimum value times the area of D. So in a single variable case, you had a property like this where the integral from a to b was bounded above by big M times b minus a, so the width of the interval, and bounded below by little m times b minus a. So it's all the same idea, just the size of whatever region you're integrating over. And finally,
Nothing's fine.
okay.
It's always changing.
Recognize that? Yes, mean value theorem. Okay. Now, I don't know if you would have been taught this in 168. Should have been. So this is the mean value theorem. So this is closely related to the mean value theorem for integrals, which says that the integral from a to b of f of x, provided that f of x is continuous, is equal to f prime. The value of f at some point times b minus a. So you can get this directly from the mean value theorem by applying this mean value theorem to an antiderivative of f, and this ends up falling out. Okay. All right. Now, for double integrals, similar results. We have the double integral of a continuous function is equal to the value of a function at some point in the region times the area of the region. Now, you don't know what that point is necessarily, but you know that it exists. Also, just for the heck of it, so okay, yes, I was lying about the finally. A close relative of the mean value theorem for integrals is the weighted mean value theorem for integrals. That the integral from a to b of a product of two functions is equal to the value of f at some point, and then you leave g of x in. provided that g does not change sign on the interval. So as long as that's the case, you're allowed to pull f out, because often this is used where g is a function that's easy to integrate, like a polynomial or something, whereas f times g is something you don't know how to do. The only reason I really mention this, of course, I end up using this a lot, but it can also be used to prove one of your favorite things from a whole calculus sequence, Taylor's theorem. All right, now.
So what is the f of c that comes out front?
So it's f evaluated at some point c.
Okay.
In the interval. Same as we have f evaluated at some point c
Right.
here, or this point here.
Okay.
Yeah. Okay. All right.
Final.
Yes, I'm done.